Well, welcome back. And today we're talking about metal reactivity. This is something we've looked at a little bit already when we looked at the periodic table and trends in the periodic table. So let's get started. Today we're going to be talking about the fact that metals and halides have varying reactivities and how we can work with those and predict them. We're also going to be looking at being able to predict displacement reactions and knowing now in terms of redox that a more reactive metal will be a stronger reductant and that a more reactive halogen is a stronger oxidant. So a non-metal being more reactive would be a stronger oxidant. Hopefully remember that the reductant is always oxidized and the oxidant is always reduced. And we're also going to look at how we can take some experimental observations and use those to determine reactivity. And finally, using the reactivity series to predict the products between metals and ionic solutions. So if I put a piece of metal into an ionic solution of another metal, will a displacement reaction happen or not? So metals exhibit a lot of common properties. We know that they're ductile, they're solids at room temperature, they're malleable, and all the things that we talked about when we looked at metallic bonding and the metallic bonding model, where we have that electrostatic attraction between cations and the delocalized sea of electrons. One of the things that we talked about that isn't explained very well by that model is reactivity, and we see a huge variation in reactivity in metals. Okay, so when we originally talked about them, we defined the metal reactivity as usually defined using its reaction with water, but we can also look at metal reactivity in terms of their reaction with oxygen when we see the formation of oxides or corrosion of metals, and also the way they react with acids. We know that a reactive metal will react with an acid to produce salt and hydrogen gas, but where exactly does that reactivity end? So we've looked at these and we've looked at the reactivity of metals in terms of a periodic table, and hopefully you can remember the trends. So have a think and let's see if you can remember those trends. So hopefully you decided that metal reactivity increases as we go down a group. So as we go down a group, we get metal reactivity increases. And as we move across a period, if you remember, we have metals on the left and non-metals on the right, it makes sense that our metal reactivity decreases as we go across the period from left to right. Hopefully we remember that. Okay, so what this means is that various metals, some are found in the Earth's crust as pure metals like gold, platinum, though not much of it, and sometimes copper, depending on the conditions. Other metals like magnesium and iron will corrode really easily, which is why we need to look at coatings on iron, why we use anti-rust, we paint things made of iron or steel, and we use alloying techniques to reduce that corrosion sometimes. And then sodium, well, sodium's kept under oil in order to keep it even away from the oxygen and water in the atmosphere. Because these metals all have very different reactivities, we need to deal with them in different ways. So group 1 and 2 metals, we know hopefully by now that these are the alkali metals. They react with water to form hydrogen gas and a metal hydroxide. These are our alkali oxides, okay? So they will form alkali metals, they're going to form a basic solution. It's highly exothermic, it occurs rapidly. That exothermic nature can actually cause the hydrogen gas to ignite when it reacts as well. Group 2 metals will also react with water, but their reactions start to get slower. And then transition metals are less reactive than group 1 or 2, with some of them being so unreactive that they're found in their pure form. So gold, in that case, we find nuggets of gold in the ground. When we look at the reactivity with acids, then we can start to see a bit of a trend. So the reactivity with metals with acids is generally greater than that with water because of that readily donatable proton. Okay, and now if you remember, we understand these as redox reactions. So that proton is going to want to join up with another hydrogen and form hydrogen gas, we're going to see a ready conversion due to redox numbers in that situation. Okay, so if we compare these relative reactivities, we can work out what we call a reactivity series for the metals. And if we have a look at this, this is magnesium, iron, and copper reacting with HCl. And you can see that the magnesium, which is one that we've done in class, bubbles quite vigorously, giving off a huge amount of hydrogen at a quick time with a high rate. Iron, the rate is much lower. We can see small amounts of bubbles there, and the copper is very slow indeed. So, like the periodic table, we can create a reactivity series which we can use to help us work out other things. And if you have a look, we've got a reactivity series over here, platinum at the bottom, going up to potassium. And this is also replicated in your data booklet, so you can use this reactivity series to help you answering questions. With oxygen, we see much the same things. Because metals tend to react quite readily with oxygen, the more reactive they are, the less likely we are to find them in the Earth's crust, because they will have reacted with the atmosphere, and they will form what we call ores. So a lot of mineral ores like bauxite, and even if you've seen that green gemstone that they make eggs out of sometimes called malachite, they're ores where the metal has combined with oxygen to form an ionic compound in the Earth's crust. Okay, so these metal oxides are then processed to find the pure metal. The more reactive the metal, the more likely we are to find it as an ore rather than a piece of actual metal in its pure form. So if we compare the reactivity metals with water, we can see that sodium and potassium will react readily with water quite violently. Okay, rubidium will explode violently. Magnesium doesn't react very well with water at room temperature, but it will react with steam, giving it a bit of extra heat to promote that reaction. And same with calcium. So if we put all this data together, again creating our reactivity series, we get this table here where we can put them in order and see that the most reactive metals down to lead and copper, these stop reacting with water and dilute acids. Okay, so we may be able to force them to react with strong acids, strong concentrated acids, but they won't react in dilute acids. Reacting with oxygen in the air, and then reaction with water and steam. Okay, so you should make yourself some study notes in regards to these as to where in the reactivity series these reactions perhaps stop. So you've got a familiarity with the relative reactivities of these metals. One of the other things, other than looking at the reactivity with oxygen or water or acids, that we can do is look at the reactivity of metals compared to each other. Now, if you think back to the demo that we did where we put the piece of copper into silver nitrate solution, one of my favorite reactions, and we see those beautiful silver crystals forming on the edge of the copper, or even back to the metal displacement reactions we did way back in the beginning of our studies in ECP and early in term 1. We know that metal displacement reactions occur, that one piece of metal can be more reactive than another and cause a metal displacement reaction. Since we've done redox, we can now understand this in terms of redox chemistry. The more reactive metal is a stronger reductant, so it will oxidize the metal in solution. So if I'm putting a piece of metal into a solution of metal ions, it will give up its electrons, okay, causing this metal to be reduced and form a solid, while the solid then dissolves into solution. So we can carry out a series of these reactions, and when we do that, we can add copper into copper 2+, no reaction will occur. If we put copper into lead, no reaction. So we can see here that copper is less reactive than any of these ions that we have here. It can't displace them out of solution. If I take a piece of lead, however, I can see that lead will displace copper out of solution, but will not displace any of the others. We can continue these reactions until we start to see that in the case of zinc, it will displace copper, lead, iron, and tin, but it won't displace magnesium, okay, which means that magnesium must be the most reactive of the metals that we see here. And it makes sense because if we look at the magnesium line here, we can see that it will displace everything except, of course, itself. So meaning that magnesium is the strongest reductant. It is able to force its electrons onto the metal ion that's in solution, therefore reducing it and losing its electrons, being oxidized itself. So if we use the reactivity series here, we can actually try and figure out predict how those reactions will go. So if we look at these solutions here, we can see we have iron plus copper 2 sulfate solution. So we find iron on the reactivity series, okay, remembering that increasing reactivity is from the bottom to the top. So iron is now, we have a look here, more reactive than copper, which means if it's more reactive, it is a stronger reductant. So iron should donate its electrons to copper, and I will form Fe2 plus in solution and get a coating of copper on the iron rod. Okay, now if we look at this example here, copper plus silver nitrate, we're now looking at copper and silver. This is the one that we've done. We can see that silver is less reactive, so the copper will go into solution forming Cu2 plus, so the solution will become blue over time, and we should see silver forming on the copper solid. Okay, I want you to pause the video and have a go at doing the next two yourself, the gold in copper 2 sulfate and zinc in iron 2 sulfate, and see how you go. Okay, so how'd you go? If we look at the example of the gold and the copper, gold is less reactive than copper. So in this case, the gold will not be able to donate its electrons to the copper, so we will see no reaction. In the case of the zinc and the iron, zinc is more reactive than iron, so we should see the zinc rod corroding and iron forming on the zinc rod. Okay, been through those. So just as a final note, we're looking at halogen reactivity. So we've looked at metal reactivity, but the halogens also can undergo displacement reactions, okay? So remembering that halogens are non-metals, so their reactivity increases as we go down the period, making fluorine the most reactive. So nothing will be able to displace fluorine, excuse me, but chlorine can displace bromine, chlorine can displace iodine, bromine can only displace iodine. And let's have a look at that. So if we have a solution of potassium chloride, nothing will happen if I add bromine or iodine into it. However, with potassium bromide, I would see a reaction where we would form brown bromine as the chlorine displaced the bromine out of solution. And then it wouldn't be able to do that with iodine because iodine is less reactive. With potassium iodide, the iodide is the least reactive of the halogens, so chlorine will displace it and bromine will displace it as well. Okay, so just remember that displacement reactions can occur with halogens as well, and we can use reactivity to predict those as well. So hopefully at the end of this, you understand that reactivity differs, that you will now be able to refer to metals in terms of being the stronger reductant and halogens in terms of being the stronger oxidant will be the more reactive species. Using experimental data to determine reactivity, so make sure you go through your textbook and do the questions on practicing those, and we'll do some practice on predicting those, and then predicting if a metal displacement reaction will occur based on the activity series. Remembering, of course, that you have an activity series provided in your data booklet. Okay, next time we'll move on and show how this term works in terms of what we call an electrochemical series. So until then, see you later.